Hi everyone, this is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we will discuss about definitions and important terminology on stress concentration. So, in design of machine elements, the stress concentration term is very important. So, based on this stress concentration, we will calculate the design parameters of a uh, different mechanical components. Whenever the mechanical components are subjected to fluctuating loads. So, what do you mean by stress concentration? So, how to reduce this stress concentration, I will explain in this session. So, whenever a machine component changes its shape of its cross section, so there is the simple stress distribution is not possible. So it means the stress distribution is not in uniform. So due to the irregularity happened. So due to the sudden changes in their cross section. So these abrupt changes of form is called stress concentration. So it means wherever the irregularity is there, is present in the component, there more stress concentration will be occurred. So generally it occurs all kinds of stresses in the presence of fillets and notches and holes, keyways, splines, surface roughness or scratches, etc. Here shown in this figure, uniform, not in non-uniform bar stress concentration. So first you take uniform bar section subjected to load. Whenever this machine component is subjected to load, so in this the stress distribution lines are uniform. So it means the stress distribution is from one end to another end is uniform. There is no bending and there is no irregularity in this uniform bar section. So for this component, you can calculate stress value. So what is the nominal stress? Nominal stress is equal to load upon area. A load is equal to applied load and area, the cross-sectional area 5/4 into d square. So this is diameter of the uniform bar. So by using this elementary equation, you may calculate stress values. But so whenever stress concentration is there due to irregularity, see in this figure, so up to here the stress distribution lines are in uniform. So here it suddenly changes direction due to this sudden changes of the shape of the cross section. So not in uniform. So up to here stress distribution lines are in uniform, so that you can apply the elementary equation to calculate the nominal stresses. But in this case, at this zone, you may not calculate. So that's why you should take the stress concentration factor. So that is theoretical or form stress concentration factor. So the theoretical stress concentration factor is defined as the ratio of the maximum stress in a member at irregularity. So at a notch or fillet, at a jumper, at a hole, to the nominal stress at the same section based upon net area. So mathematically, the theoretical stress concentration factor you may represent maximum stress to nominal stress, or you can say here localized stresses upon nominal stresses. So nominal localized stress or a nominal stress. So these so take maximum value of these localized stresses. So this value, see, the localized stresses are obtained from a stress concentration area, and nominal stress obtained from non-stress concentration area. So you may represent Kt is equal to, you may denote it with Kt, maximum stress upon nominal stress. It gives theoretical stress concentration factor. So example, the previous diagram, uniform, non-uniform bar cross section, whenever subjected to load, at this area, localized stresses will be induced. In this area zone, nominal stress will be occurred. So calculate those stresses and take the ratio, and you will get stress concentration factor. So if you know the nominal stress, clear. So otherwise, if you know the theoretical stress, suppose you have taken, you have assumed the theoretical stress concentration factor some value, so you may calculate other stresses. So what are the factors to be considered while designing mission parts to avoid fatigue failure? So what are the factors? The main factors are, while considering or designing mission parts to avoid fatigue failure, the variation in the size of the component should be as gradual as possible, and the holes, notches, and other stress risers should be avoided. And the third point, the proper stress deconcentrators such as fillets and notches should be provided wherever necessary. So stress deconcentrators. So reducing methods, these are fillets and notches and holes. So we'll explain. So similarly, a smooth finish of outer surface of the component increases the fatigue life. So surface finish factor also very, very important while calculating the fatigue life. So already we have discussed in earlier sessions. So the material with high fatigue strength should be selected, and the residual compressive stresses over the port's surface increases its fatigue strength. So the fatigue failure, fatigue strength depends upon the material and the type of loading. So the material means the type of surface finish and what is the size of the component. So depends upon all these factors. So here one more factor is there, that is fatigue stress concentration factor. So in previous case we have studied theoretical stress concentration factor, and then what are the important factors considered while designing machine parts to avoid fatigue failure, and here given the material with high fatigue strength should be selected, and shown in this diagram 1 and 2 and 3. So here, see the cross section here, and slightly curved one, this one, and in this there is no curvature. So due to this irregularity, see in this some notch is there, and here some fillet is there in this component. Here again fillets are there. So due to this irregularity of the component, so some stress concentration will be induced in the component, in the machine component. So due to this stress concentration, the component will fail. So how to avoid this stress concentration factor? Some reducing methods are there. So we'll explain in later slides. So fatigue stress concentration factor, when a machine component or machine member is subjected to cyclic or fatigue loading. Cyclic or fatigue loading, the value of fatigue stress concentration factor shall be applied instead of theoretical stress concentration factor. The stress concentration factor Kt, theoretical stress concentration factor. Kt, Kt is equal to maximum stress upon nominal stress. So here, the fatigue stress concentration factor, endurance limit without stress concentration factor upon endurance limit with stress concentration. It gives fatigue stress concentration factor. Endurance limit without stress concentration factor. Endurance limit with stress concentration. So Kf is equal to sigma E without stress concentration and upon sigma E with stress concentration. With stress concentration. So another term is there. So this term is very useful for calculating fatigue stress concentration factor. Notch sensitivity. So you may denote it by Q. So the term notch sensitivity is applied to this component behavior. So it means it is defined as the degree to which the theoretical effect of stress concentration is actually reached. So whenever the component is undergone stress concentration, so what is the value? What is the magnitude? That means what is the degree? What is the behavior of the component under stress concentration? The stress gradient depends upon mainly on the radius of the notch, hole or fillet and grain size of the material. So here the Q notch, when the notch sensitivity factor Q is used in cyclic loading, then fatigue stress concentration factor may be obtained by using the following relations. I will write here. Kf is equal to maximum stress upon nominal stress. Kt, endurance limit without stress concentration factor without stress concentration upon sigma E with stress concentration. With stress concentration. So now, in terms of Q is equal to Notch sensitivity Kf minus 1 by Kt minus 1. So now, by using this Notch sensitivity relation, you may determine Kf and Kt. So Kf is equal to Kf minus 1 to Q into Kt minus 1. Kf is equal to 1 plus Q Kt minus 1. So that the fatigue stress concentration factor is equal to 1 plus Q multiplied with Kt minus 1. So this is the relations between fatigue stress concentration factor, theoretical stress concentration factor, and Notch sensitivity. Next here, shown the combined steady and variable stress. So before going to enter in this topic, so I will explain reducing methods. Stress concentration reducing methods. Reducing methods. So one is by creating extra walls in the component, you may decrease the stress concentration value, and by creating notches and some fillets, you can reduce the stress concentration value. So it means, so you can't eliminate the stress concentration value permanently, but somewhat value you can reduce. So that's why I always use this wherever stress concentration is present, there you can apply these reducing methods. Suppose in this cross section, subjected to axial load, so this subjected to load. So here stress concentration will be occurred. We want to reduce this stress concentration, so that create fillet with some radius. Due to this fillet, the force carrying lines are bended like this. So you can reduce the bending area of lines. Due to this, the stress concentration value will be reduced at this local area by creating fillets with radius R. So previously this one is very corners are sharp edge, now converted into curvature. So like this, the stress distribution is possible. So this is one method. You can create fillets, chamfers, and extra walls also. Suppose this shaft, some here discontinuity is there. So due to this discontinuity, a stress concentration will be occurred. So up to here uniform, and the, the stress distribution lines are uniform. Due to this irregularity, stress concentration will be high. So to avoid stress concentration, so by creating extra walls, already this is the previous wall, so you may create another 2-3 walls. So due to this wall creation, the stress distribution band lines are formed like this. So creating extra walls. This one extra walls. These two are walls. So like this also you can reduce the stress concentration. One more method, notches. You may create notches. So again you take a uniform bar section. So at this, so again the wall is there. So you may reduce the stress concentration by creating extra notches like this. Like this. So you may create notches. So due to this notches, the smooth stress distribution is possible. So these are the reducing methods. Next one is important um, important topic, combined study under variable stress. In this, three formulas are there, three empirical relations are very useful for problem solving whenever the object is subjected to combined steady and variable stress. So by using this diagram, this diagram drawn variable stress to mean stress. So in this x-axis shown sigma y and sigma u, and y-axis sigma e, the endurance strength. So remaining these all are failure points. First you take Soderberg line method. In Soderberg line method, So 1 by factor of safety is sigma m by sigma y plus sigma v by sigma e. And the Goodman line method, 1 by factor of safety sigma m by sigma u plus sigma v by sigma e. And Gerber parabola, 1 by factor of safety sigma m by sigma u whole square into factor of safety plus sigma u v by sigma e. So these are the empirical relations for Soderberg, Goodman and Gerber parabola to calculate the mean stress values and independent stress, variable stresses value. So the mean stress is equal to sigma max plus sigma minimum by 2. The variable stress is equal to sigma max minus sigma minimum by 2. So the Soderberg line theory line is used for ductile materials. The Goodman is used for brittle materials. Gerber also used for ductile materials as well as brittle materials. This here shown the factor of safety value, the factor of safety. So already you know the factor of safety is a safety factor to avoid failures. How to use for design of machine components. This factor of safety value you may calculate by using maximum stress and design stress. It is the ratio of maximum stress to design stress or working stress. So these three are empirical relations for commercial and variable stress calculation. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.